So can you type here what is the meaning of isoelectronic species? All of you please try to type meaning of the isoelectronic species. Iso means same. Electronic means, yes, what is the meaning of isoelectronic species? Ashita, Lavanya, Sanjana, please answer it fast. Isoveer, isoelectronic species. Same number of electrons. What does it mean? It means same electron configuration. Yes. Isoelectronic species have same number of electrons and they have same electron configuration. Yes, Ashita, very good answer. Okay, so now I'm taking you on the periodic table and we'll discuss the size of ions, different ions, based on the charges present on them, based on their electron configurations. So I'm giving you a list of ions here. N3 minus, Al3 plus, neon, Mg2 plus, F minus, Na plus, O2 minus. Let's write down their electron configurations. So before you start writing the electron configuration, you see where are these elements? Nitrogen, oxygen, fluorine, neon, sodium, magnesium. Now based on the charges on them, so can you tell me how many electrons are here in N3 minus? How many electrons are there in N3 minus? 10. In Al3 plus? 10. In neon? 10. In Mg2 plus? In F minus? In Na plus? In O2 minus? See, are they isoelectronic, children? They should be isoelectronic. So we can write down one electron configuration for all of them. What's the configuration? Write the configuration for these 10 electrons, which will be identical for all of them. So Sanjana and Dhruv are saying neon. Yes, neon. So number of shells in all of them. Neon, you see, neon is in the second period. It is actually 1s2, 2s2, 2p6. How many shells? 1 and 2. Veer, you know Bhavya? Veer, you're there? Okay, can you just send a message to her that she has not joined the class? Thank you very much. So 1s2, 2s2, 2p6. So there are two shells, right? Two shells. So all of them have two shells. So do they have the same size then? Do they have the same size? Veer Bhavya is here. Thank you very much, Veer. No, they don't have the same size. Why? Because electrons are 10 in every electron configuration. Electrons are 10, but what are the protons? Can you tell me the protons in every case? Protons, the nuclear charge. Nitrogen, 7. Aluminum, 13. Neon, 10. Magnesium, 2 plus. 12. Number of protons are different. Fluoride, this is fluoride, 9. Sodium plus, 11. O2 minus, 8. Yeah, good. Now, you remember that I told you when you are going to discuss the size, you have to take care of the number of shells and effective nuclear charge. Now, can you tell me, because electrons are same, but number of protons are different, then which one has the highest positive charge in the nucleus? Which one? Al3 plus. So, highest Z effective. Can I say that? Highest effective nuclear charge. So, it means this one is going to pull the electron density more strongly. So it's going to be smallest in size. Agreed, children? Smallest in size. Anyone has any doubt that Al3 plus is smallest in size? Which one is biggest in size? Now your turn. Which one is biggest in size? Shivani, Sanjana, Dhruv, they are saying N3 minus. Can you give me the reason? Bhavya is also saying the same thing. Can you give me the reason, children? Veer, you are back? So give the reason. Because N3 minus has minimum nuclear charge. Lowest Z effective. Very good language, Bhavya. So, minimum attraction, minimum pull. I hope you are understanding the pull. This is the nucleus, and the nucleus has an electron cloud around it, like this. Like this. If nuclear charge is very high, then they will pull the electron density. This is the nucleus, and nuclear charge is high, so electron density will go more closer to the nucleus. See, this will result in shrinking. More attraction, more shrinking of the size. So very good. Now we have understood that how to arrange these isoelectronic species based on their nuclear charges according to their sizes. So let's start with the smallest and go to the biggest. Ready, children? Smallest. Which one is smallest? Starting from the smallest to biggest in size. I hope my question is clear. Smallest to biggest in size. Al3 plus. Smallest. Next. Veer Mg2 plus. Not 1 plus, right? Next. Na plus. Next. Neon. Next is neon. Very good. Next. F minus. Lavanya, you are understanding? Veer F. Then next is O2 minus. Next, N3 minus. So Al3 plus is smallest, Mg2 plus. Is it okay? Children, those who are not appearing for AP Chemistry this year, there is no compulsion of doing quizzes on the website. You just come for the classes, do questions with me here in the class. Okay, try to learn things properly. Do questions. Recordings and quizzes will be available to you next year also. Then you can, through the summer vacation, practice on your own, right? And I will be in touch. You can use forum to ask questions. So don't come under pressure from the quizzes or the website. But those who are appearing for AP this year, I request them to start doing it. Yes, you can do it. Yes, yes, Anna. You can do it even if you are not doing AP. But some children, they are coming under pressure that they are not doing quizzes, so they have this guilt. So, and I just want to clarify them. If they are not doing, if they don't have AP this year, if they are not doing, I have no problems. But if you can do, there's nothing like that. It will be really good if you do when you are learning and do it. Learning, do it. That is the ideal way of learning. But if you are unable to do it, that's fine. But for AP students, those who are appearing AP this year is compulsory. They must do it from my side. Okay, so we are okay with this? One last question. This is a very popular question. That's why I'm giving time to this question. One last question. I'm giving you some examples here. P3 minus Ca2 plus S2 minus. Just start working out their number of electrons. Cl minus K plus Sc3 plus and Ar. Can you tell me number of electrons in all these ions? How many electrons? They all are 18. Sanjana, perfect calculation, very fast. Check it, children. P is 15, 15 plus 3, 16 plus 2, 17 minus 17 plus 1, 19 minus 1 because it's K plus, right? 20 minus 2, and this one is 21 minus 3. Now I'm giving you few minutes, maybe 1 minute only, okay? Can you write down these isoelectronic species in the increasing order of their atomic size, ionic size? Start with smallest. They all have same electrons. They have the same electron configuration. So just work with their nuclear charges. Start with smallest, go for biggest. Veer, now you can hear me? Can you hear me? Yeah, so I was not speaking when you said I can't hear you. I was quiet. I'm waiting for the answer. There's an error in your answer, Shivani. Correct it. Oh no. Sorry, Shivani? No. Your answer is perfectly all right and is very fast answer. So thumbs up for Shivani because she has used a trick. That's why. You can answer it very fast because the one with highest positive charge should be the smallest and the one with highest negative charge will be the biggest. So today I'm going to introduce you with one new term. Try to learn it today only. This negative charge means, like in case of P, it has gained 3 electrons, right? So the configuration is 1s2, 2s2, 2p6, 3s2, 3p6 for this p3 minus. So 3 electrons are added in the outermost shell. This is outermost shell, the valence shell, outermost shell. Yeah, your answers, all of you are giving me right answer. So children, please understand the one with the highest positive charge, smallest. The highest negative charge, biggest. Now I'm giving you one more reason for the bigger size of anions. This is an anion, right? Negatively charged. So let's try to understand why these anions are bigger. One reason is clear to us that they have less nuclear charge. But another reason that when you are adding electrons, adding 3 electrons, 2 electrons, 1 electron, will create inter electron what? Repulsion or attraction? Electrons will repel or attract, children? Coulomb's law. Like charges, they will repel. These are like charges. Inter-electron repulsion. Learn this word. Many things can be understood by this method. Inter-electron repulsion. So inter-electron repulsion, when this is happening, what will happen? Electrons would like to come closer or would like to go away. Electrons would like to come closer or would like to go away when they are repelling away. So Bhavya, very good. So when these electrons are going to repel, they would like to move away. And due to this, there is expansion of size. Expansion of size, like P3 minus. I'm making P3 minus here, children. This is P3 minus. I'm making S2 minus. This is S2 minus. I'm making Cl minus. This is Cl minus. This is the expansion of the electron cloud. Expansion. They need more space due to high. This is P3 minus, children. P3 minus. This is S2 minus. And this is Cl minus. This is high inter-electron repulsion. Inter-electron repulsion because there is more negative charge. So understand P3 minus is a stable configuration. Agreed? Fully filled, stable. But still, it is reactive because it has so much negative on its head. So ions P3 minus is stable configuration, but due to high electron density, it is reactive also. It would like to have, so P3 minus is comfortable with something like K3P is comfortable with this. Why? Because these are plus 3, this is minus 3. So minus and plus are happy together. Attraction, more attraction. So they try to, this P3 minus will search for attraction. Okay. So are we clear about the inter-electron repulsion? So I can move on now. Isoelectronic species, inter-electron repulsion, their charges and size of the anions are always bigger because of the inter-electron repulsion and less nuclear charge. Moving on, children, coming on this presentation again, teaching you the next concept. See here, these are the size of ions. A beautiful representation. These are the examples you did with me. N3 minus, O2 minus, F minus, Na plus. This example we did, isoelectronic series. Remember, this was neon, neon. 10 electrons, all of them. 10, 10, 10, 10, 10. This is how you can make isoelectronic species. This one. Up to here, aluminum 3 plus. And then another isoelectronic species, S2 minus, Cl minus, K plus, Ca2 plus. This is of 18 argon. We just did it. P3 minus is missing. So can you answer my question? This P3 minus will be bigger than this or smaller than? It will be bigger. Another question, children. Another question for all of you. Pay attention. Okay, the question goes like this. As I'm moving down here, is the charge changing, the negative charge? No. But the size is changing. Why? Down the group, you can see size is increasing. So give reason for the increase in size. Yesterday I told you two reasons for comparing sizes. One is shell numbers Second is Z effective, yes. So what is happening to the number of shells as you are moving down? Oxygen has how many shells, children? This oxide? Two. This one has three, four, five. So number of shells are increasing. Size definitely going to increase. More shells. And if you remember, more shielding is also there. Shielding, remember Z effective. So shielding is also increasing as shells are increasing because more inner electrons. Inner core is becoming bigger, bigger, bigger with more electron density. So more shielding. More shielding means Z effective is going down. Nuclear charge felt by the outermost shell electrons is less, is decreasing because in between the outermost shell, this is the nucleus, this is the outermost shell. If you increase the electron density between these two, the nuclear charge is getting screened, shielded from the outermost electron. It's not enjoying the full attraction of this nucleus. So this is what we did yesterday. I think we are clear about it. Ready for new topic, children? This is the most important thing what we are learning. Very important. I have seen college students asking stupid questions because their basics are missing. I don't want you students to be like those children, and it's not their fault because we have to make our students, children understand what is important and practice it more. Periodicity. If you master this, you don't require any teacher for explanation in organic chemistry. You have to just focus. You can read the book and you can understand what is happening. Next important thing we did Z effective, we did size of neutral atoms and ions. Third, ionic sizes. These three trends we have already done now. We are coming on the fourth one, which I will be writing as IE, ionization energy. So let's try to understand the word ionization energy, the word. This is the nucleus and this is the electron. Electron and nucleus are attracted to each other. Depending upon the distance of the electron from the nucleus, screening, shielding, all these effects are there. Attraction will be high or less, but attraction is there. Now, if I want to remove this electron, let's say this is A element, I want to remove this electron. So when I'm removing the electron, A will get converted into A plus. An electron is out. Let's say there is another shell here. So only one shell is left. An electron is out. You can see I have reduced the size A to A plus. What is happening? Size is decreasing, right? Size decreasing because you are removing a shell here. Effective nuclear charge is increasing. There is plus charge on it now. Electrons are less, protons are more. Protons are not changing, but here electron and protons are equal. Let's say 10 electrons, 10 protons. But here 9 electrons, 10 protons. So can I say the ratio is changing, right? Electrons are less, protons are more attraction. The plus charge is indicating more attraction, high effective nuclear charge. This is called as ionization. During this ionization, A is converting to A plus. Ionization. The word is ionization. You have done this word earlier also when we were doing unit topic 1.2. That mass spectrum, mass spectroscopy for identification of the isotopes. At that time, I told you this ionization word means removing electrons. Now this removal of electron, do we need energy or energy is released? Removal of electron, breaking of attraction. And breaking of attraction is breaking attraction is endothermic. Endothermic means heat. Endo means in. Thermic means heat. Heat needed. Where it is heat needed. I gave you the mantra. Write down this, Veer. When you are breaking a stick, if I give you a stick, if I ask you to break, you need energy to break it. Breaking needs energy. Energy absorbed. Okay, Veer? It's not energy released. You are getting it? Write it down. Because the error which you have done, you may repeat it. Because sometimes something goes in the wrong way in the head, it keeps coming up with the same answer, energy release. I've seen children. So just think strongly, write it down, and try to settle it in your head. So we are okay with this? So breaking attraction is endothermic. And making attraction, children, write down this. Making attraction. When attractions are made, nature wants attraction. Making attraction is always exothermic. Exothermic. And heat released. So write down these two terms. We are going to use them here. Is the word ionization clear to everyone? Okay. So ionization energy is the energy required, needed to remove an electron from gaseous atom, isolated gaseous atom. By definition, isolated gaseous atom by definition. Why? Because if I give you sodium solid, it's not gas, right? Solid, like this. This is sulfur. Sulfur is of this color. It is solid under normal conditions. This is sulfur. If I give you sodium solid and you supply heat, add heat, what will happen first? First, the sodium will get converted into liquid because it needs less energy to break the attractive forces and it will become liquid first. Then it will become gas. So first it will undergo a physical change. So this I cannot say that this is ionization energy, the energy needed here. This is delta H of solid to liquid fusion. This is not ionization energy. They have other definitions. Liquid to gas, delta H. Delta means change, H means heat. Liquid to gas, vaporization. And once it is in the isolated gaseous state and you are still supplying heat, heat is still added, then it will undergo ionization. That heat will remove the electron from the gaseous atom. And this energy is called as ionization energy. Anyone has any question here? So by definition, only this process represents ionization, not these. They have different definitions. Up to here, something else is happening. So I don't want to include these heats in my IE. Is it okay? Definition is clear, children, to all of you. Okay, now my question starts. So if my question is not clear, you can write here, not clear, speak again. I'll speak again, okay? Here is the question. There is a big atom and there is a small atom. The electron is here in the big atom and the nucleus is always in the center here. And there is attraction between the electron and the nucleus. This is small atom, electron is here and nucleus is here. Remember Coulomb's law? F equals to K times Q1 Q2 over R squared. If this is A is big atom and B is small atom, can you tell me in which case the electron is more strongly attracted to the nucleus and why? Why? The electron is more strongly attracted to the nucleus. Okay, Dhruv is saying B, Veer is saying B, Dhruv is answering, Shivani, yeah, Bhavya. Because this is R here. R means distance or separation. Here R is less. If R is less, attraction is more. Is more closer. Yes, very good. Is it clear to everyone? Ashirta? Arnav? Arnav, you're answering okay. Mhm. Lavanya? Lavanya, you're there? Okay, good. So attraction is more in the B, right? In which case it is more hard to remove electron. In which case it is more hard to remove electron. B, very good. In which case ionization energy is high. See? So can I say big atoms will have less ionization energy and small atoms will have high ionization energy? Can I say that? Okay. Let's go to the periodic table and let's discuss ionization energy down the group and across the period. Okay, so it depends on the size. Now you have seen that, right? So down the group, top to bottom, what happens to size in the group? What happens to size? Down the group, what happens to size, children? You remember? Size increases or decreases? Increases. Size increases. Across the period, remember across the period, there is no increase in the number of shells, but Z effective increases. So there is a decrease. Yeah. Yes. So this we have done in the last class. Ionization energy depends on size. So one factor is it depends on size. So what happens to ionization energy down the group? Ionization energy in a group increases, decreases. Oh, you have answered? Down the group, size increases and ionization energy decreases. We just discussed this. If size is small, attraction is big, attraction is less. So down the group, as the size increases, ionization energy decreases. Agreed, children? Okay, good. Now across the period, size decreases. If size decreases, attraction of the electron with the nucleus increases. Ionization energy increases. We are okay with this? You can memorize it right away, right? So ionization energy depends on the size, and down the group size increases, attraction decreases, ionization energy decreases. Across the period, size decreases, attraction increases, ionization energy increases. This is one factor. And this will give you a regular trend. This is normal trend, regular. We are expecting this. But there is another factor, stability of electron configuration. This will give you exceptional behavior, exceptional jumps. We call it as exceptional jumps. Now let's talk about this stability of electron configuration. Okay, down the group, the configuration is changing. Is it becoming more stable, exactly half filled or fully filled or noble gas configuration? Like what is the configuration in the first group, general configuration? NS1, the outermost shell of all these elements have one electron. So the stability is not changing. It is 1s1, 2s1, 3s1, 4s1, 5s1, 6s1, 7s1. So their stability means exactly half filled or fully filled. Are they becoming like this? No. Same, correct? Same one electron in the outermost shell. So stability of electron configuration in the group not valid. So do not worry down the group, because if this is NS1, all of them are NS1. If this is NS2, which is stable, fully filled, but all of them are NS2 down the group. So down the group, the general electron configuration is not changing. The stability of electron configuration is not changing. So the factor is not valid. So you will say no exceptional behavior, no exceptional ionization energies. It's a regular trend. Down the group decreases. Irregular trend. Anyone having any trouble till now? Are you clear that down the group electron configuration, general electron configurations are same? So there will be no exceptional values which will not fall in the regular trend. You will not see anything like that. If I ask you to make the graph, here is the atomic number. Here is the ionization energies. So the highest is for hydrogen. This is hydrogen. Then lithium. Then sodium. Then potassium. Then so on, right? Irregular trend, irregular. The graph is a line going down from element number 1 of the group to the last element. No exceptional behavior, okay? But across the period, let's move across the period. Let's pick up period number 3. This period, 3. Sodium, if you see the sodium, its electron configuration is neon, 3s1. Magnesium, neon, 3s2. Aluminum, neon, 3s2, 3p1. Out of these three, which one is stable? Which one is stable? You remember exactly half filled, fully filled are more stable than partially filled. So which one is more stable? Sodium, magnesium, or aluminum? Mm-hmm. Bhavya, it's a very simple question. Arnav, these configurations are not same. Sodium is this. Am I audible, children? No, I'm not audible. I'm audible. Okay. They are not same. Okay. Because, okay, you remember that exactly half filled is valid only on degenerate orbitals. We did it last time, last to last class. Degenerate means on the p subshell and d subshell and f subshell, not on s, not on s, Arnav. So you cannot say this is exactly half filled. Don't consider because s has only one orbital. There is no degenerate orbitals. So this is not stable, not stable. This one is stable, fully filled, and this one is not stable, partially filled. So you're forgetting about that. So please write down that exactly half filled, which we have done earlier also, which is valid only for P, D, F, and fully filled are more stable. Exactly half filled or fully filled are more stable, right? So which configurations are exactly half filled and which configurations are fully filled? You know their general configuration, NS1, NS2. So this family is fully filled. Agreed? Yes, Veer. This is NS2 and P1. So here which family is exactly half filled? Can you work out, children? This family. What is it? NS2 and P3. Yes. And which family is very stable? This one. So across the period, when you are moving across the period, let's say period number 3 again, as I go from sodium to magnesium to aluminum, the size is decreasing. So ionization energy must increase as size is decreasing, right? Because size decreasing, attraction increases. But exceptional jumps will be there. See how. Which one should have the highest ionization energy in period number 3? Highest. Argon, because it is on the extreme right side and it is a fully filled stable configuration. So argon is on the top. Highest ionization energy. It is here on the top. This is argon. And here is the atomic number. Argon has the highest atomic number, right? See, 18. Let's say this is 18, argon. And which one you're expecting lowest? Sodium. Biggest in size? Sodium. Sodium is here. Let's start with sodium here. Then magnesium. Magnesium should be higher, right? Magnesium is higher than sodium. Smaller size. Stable configuration. Then aluminum. You know, children, this is magnesium. This is sodium. Aluminum is lesser than magnesium. That's the exceptional behavior which you need to know. Where you are back. This is aluminum. This is exceptional. Can you see? There is a drop. Why there is a drop? Because magnesium configuration is neon 3s2, but aluminum configuration is neon 3s2 3p1. It's difficult to remove electron from here. It's stable. But it's easy to remove electron from here. Why? Because once I remove the electron, then it becomes stable, fully filled. So aluminum is willing to give away one electron, more, more willing as compared to magnesium. Okay. So this is magnesium and this is aluminum, right? After aluminum, silicon. Silicon is higher than aluminum because it's smaller in size. Then phosphorus. Phosphorus is higher than silicon, smaller in size, regular trend. Then sulfur. Now let's compare phosphorus with sulfur. Phosphorus is P3, stable. Sulfur is P4, one more than stable. So it is willing to give away one electron. So its ionization energy is less. Sulfur is here. So across the period, these exceptional jumps are there. Sulfur is less than phosphorus, then chlorine, and then argon. Can you see this exceptional behavior from second group to third group? When I'm moving across the period, when I go from second group to third group elements have less ionization energy than second. Fifth group elements and sixth group, you can call it as 15 or 16 or fifth or sixth. 16th or sixth group elements have lesser ionization energy than fifth due to stable configurations. Exactly half fill and fully fill. So I try to explain you very clearly that down the group need not to worry about exceptional behavior because configurations are nearly same and stability is same. But across the period, ionization energies will show you exceptional jumps when you go from stable configuration, like configurations are changing. If configurations are changing, so in between, you are coming across to some configurations which are very stable. So they will show you exceptionally higher ionization energy than from the next family, like this one. Okay, children, ask your questions if you have questions. You have any questions here? No? Okay. Then can I ask questions? Okay. Answer my questions. So ionization energy depends on two factors. What are those two factors? One factor is size. Second factor is stability of electron configuration. Second factor will show you only exceptional jumps across the period. Is valid only on across the period. Second factor is for exceptional configurations across the period. Size is the only factor down the group. This factor, second factor, is not valid across the period. So that's the review. So tellurium and sulfur, which element will have higher ionization energy? Okay, good, very good. Because sulfur is smaller in size, tellurium is bigger in size. They are in the same group. So I'm not looking at the second factor. Okay, next question. Nitrogen and oxygen, which one has higher ionization energy? Nitrogen and oxygen. Now you're moving across the period. Take care of both the factors. Yes, Sanjana, very good. Nitrogen, because nitrogen configuration is 1s2, 2s2, 2p3. And oxygen configuration is 1s2, 2s2, 2p4. So you will see that this family will have lesser ionization energy than this nitrogen family, always. And this family, this one, boron family, will have lesser ionization. So there are plenty of questions based on it. Ready for one more question? Try to answer this question, all of you, please. Okay, magnesium with aluminum, which one should have higher? So you're moving across the period. Magnesium. So I think it's clear to all of us that exceptional jumps also. I'm going to show you here a graph of atomic number versus ionization energy. This one. One second. My mouse is not in my control. Oh, oh, something happened. Am I sharing something? Is still the periodic table or the presentation? The presentation. Okay, I want to make it full. Let me see if I can do it. Yeah. This one. Okay, children. This is a group. This is a period. This one. First period, helium. Check your periodic table. Helium has the highest because it's inert gas configuration. Can you see all the noble gases are on the top in their respective periods? This is period number 1. This is period number 2. Can you see in period number 2 exceptional jumps? This one. You can see that this is lithium, this is beryllium, this is boron, carbon, nitrogen, oxygen. Oxygen has less than nitrogen. And this one is fluorine. Period number 3, exceptional. You can see the jumps here. Sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, argon. After that, period number 4. Can you see so much exceptional? This is 3D. D block has introduced. D. This is F. F is introduced. F here also. Here also it is introduced. So when D and F are introduced, then you can see so much anomalous behavior also, right? I think, yeah, F is not here. In this case, there is no F in rubidium. It is D only. This is 3D, this is 4D, this is 4F, this is 5D. So when D orbitals are introduced, nobody is going to ask question from there. So basically, you have to learn everything from period number 1 to 3. For rest, they may ask only general question like krypton is highest, why? Fully filled, stable configuration. Any questions in this graph? This is ionization energy. This is atomic number. Ionization energies, they have a unit of kilojoules per mole. That's how we measure them. How much energy is needed to remove electron from 1 mole of the element? Kilojoules per mole. We are good with this? Now I'm taking you on the next important concept of ionization energy, and that is successive ionization energy. Successive. The word is successive. When you remove first electron from the element, you get a plus charge. But when I want to remove second electron and third electron, so here I'm removing second electron, 2 plus. When I'm removing third electron, 3 plus. We call it as ionization energy 1, 2, 3, like this. So if I give you X, X plus, X2 plus, can you tell me how the nuclear charge is increasing? Effective nuclear charge, Z effective. Is it increasing or decreasing? You know that you are removing electrons, electrons are becoming less. So there is more attraction. More positive, more attraction. Z effective is increasing. This is the trend of Z effective, is increasing, Lavanya. More positive, more attraction. More attraction means more effective nuclear charge. Lavanya. Are we clear about it, children? Any question here? So now tell me one thing. In which case it is more difficult to remove electron? In X plus, or in X2 plus? In which case it is more difficult to remove electron? Answer it. I think children, you are getting confused. Okay, why? Only Veer is right. I'm asking out of these three, in which case it is more difficult to remove electron? It is from the one which has the highest positive charge, because there is more attraction. Dhruv, you are getting it? More attraction, more difficult. Don't go away from this simple concept, attraction. If attraction is more, then more energy is needed. More energy is needed, then high ionization energy. So which ionization energy is highest? Third. See, third is highest. Because third is removed from the element which already has 2 plus charge on it. First, from the neutral atom. It's easy. But when this atom is converted into ion, then it becomes difficult because attraction is more. Is it okay, children? Okay. So those who answered it wrong, I think they have understood this. Very good. Okay, I have few questions. Al3 plus, Al and Al2 plus. Can you arrange them in their order of ionization energy? Like in which case it is most difficult, so that is highest. In which case it is easy, that is lowest. Can you tell me which one is going to have the highest ionization energy? Yes, Al3 plus will have the highest, then Al2 plus, then Al. I think this is clear to us, right? Ready for next thing on the ionization energies? Next. What you are learning here is going to help you in learning the next concept, that is electron affinity. In the ionization energy, I told you the exceptions, right? Similarly, in electron affinity, exceptions will be there. But before we go to the next electron affinity, there is one more thing, one more important concept left in this ionization energy. Let's do that. Okay, let's pick up aluminum. Can you give me the configuration of aluminum, children? Neon, 3s2, 3p1. Remove first electron. Remove one electron only. So 1 plus. What's the configuration here? And this is ionization energy. First ionization energy. What's the configuration? Neon. Yes. I removed one electron from the outermost shell. Means 3p1 is removed. 3s2. Configuration of the ions. Is it okay? If you have understood this, remove another electron. Second electron. IE2. Remove one more. That will give you Al2 plus. Can you give me the configuration of this one? Ashita, this one. I removed one more. Yes, very good. Neon, 3s1. Remove another electron. Another. Al3 plus. What's the configuration? Neon, very good. Remove another electron. You can keep removing successive. There are, how many electrons are there in aluminum? 13. Keep removing one by one like this. Keep removing. So aluminum 4 plus. This is IE3 and this is IE4. I'm removing fourth electron. I have to break this inner core and it becomes helium 2s2. Yes, throw. Perfect answer. 2p5. Bhavya, you're getting it? Okay. So I'm not going to remove all 13, but I'm telling you that you can keep removing one by one up to 13. Now let's compare. Which one is highest here? Highest ionization energy. Successive ionization energy. Definitely IE1 is the lowest. Then, okay, Bhavya. IE2, then IE3, then IE4, then IE5, and so on, right? So I'm not showing IE5. We are okay with this because as the positive charge is increasing, the attraction is increasing, more energy is needed to remove the electron. Simple like this, right? Okay. But when this one is going, there is a ionization energy which is extremely high, extremely. Which one is that? It is extremely higher. It falls in the regular trend, but is going to be extremely higher. It's going to show you, we call it as big jump. There's a big jump of ionization energies. Where? Don't you think here, from here, this one? It's very difficult to remove electron from neon, isn't it? So going from neon configuration to this one, breaking an inert gas configuration needs a big jump. So after removal of 3 electrons from aluminum, means after removal of all the valence electrons, this 2 plus 1, 3, these are valence electrons. You remove the valence electrons and you can see that you are with the inert gas configuration, and then there is a jump of thousands and thousands. I'm going to show you that jump here. Bhavya, you're back. This is important, children. Let's see this. Let's talk about lithium. Lithium configuration is helium 2s1. Remove first electron, this electron. This is the ionization energy. When you remove first electron, you are going to hit the inner core. This is the inner core. Can you see the jump of thousands and thousands? Very first big jump, thousands and thousands. This is big jump of thousands. Ionization energy increases from 520 to 7,300. I'm going to call it as big jump. Let's see beryllium. Beryllium is helium 2s2. Remove first electron, helium 2s1, IE1. Check the value. 899. IE1 first. Remove second electron, IE2. Check the value. 1757. It's not a big jump. Remove third electron, IE3. It becomes 1s1. Can you see the big jump, children? Big jump. Is it okay? Anyone has any confusion? You can see the big jump, right? Okay. Can you tell me where is the big jump in this boron family? Just check. Which ionization energy is showing you big jump? The fourth. In carbon family, where is the big jump? In fifth. Can you tell me how many valence electrons boron has? Look at the periodic table. Check valence electrons of boron. 3. That is the reason After removal of the valence electrons, the valence shell is completely removed and you are going to hit the inner core. The helium, boron has helium, right? Helium core. You are going to hit that. So this big jump is going to tell you the valence electrons. I'm going to hide these elements here now, children. Let's see where is the big jump here in this case. First big jump. First big jump. Yeah, in this case. Mhm. First big jump of thousands. After removal of these two electrons, correct? The third ionization energy. Yes, Ashita. The third. So how many valence electrons this element has? This element has how many valence electrons? Two. These two. After removal of two valence electrons, you are going to hit the inner core. That's why the third is so high. Dhruv, you are getting it? Children, this is okay? So write down this. Removal of valence electrons results in inert gas configuration, which gives you a big jump in ionization energy. If this element has only two valence electrons, because after removal of two, IE3 is big jump, big, very big. So it means it has only two valence electrons. So it belongs to which family? Is it family 1, family 2, family 3? Which family? Group number 2. So this element is from group number 2. You want to see? Please write on this. Children, those who are not interacting, I just want to be sure you're understanding this. I'm going to clear it. See, I was talking about this one. Family number 2, check the alkaline earth metals. Calcium. Family number 2. Arnav, you have your periodic table next to you? Arnav, all of you have your periodic tables because we are learning periodicity. So I want you to have 3, 4, 5, whatever number of printouts. So you can make brief notes the way I'm on the side of that printout here and there. Okay, can you see this? Why? Because if you look at the configuration of calcium, please children give me the configuration of calcium. Look at your periodic table and all of you please write down the configuration of calcium. Yes. So what is the valence shell and valence electrons? Okay, now answer this. Now answer this question, children. Those who have not answered the electron configuration, don't worry. I think it's clear. Now, how many electrons, after removal of how many electrons you are going to hit this argon? Removal of 2. So it means IE3, removal of third electron, is difficult. So there is a big jump. See? Removal of first, second is higher than first because nuclear charge, effective nuclear charge is increasing. But removal of third is very difficult. Stable configuration. So that is the reason from the jump, from the big jump, you can identify the valence electrons. And from the valence electrons, you can identify the group number. If you see, second family is Ns2, two valence electrons. Third family is Ns2 and P1, three valence electrons. So ready for a question, children? Ready? Now I'm asking a question. Pay attention. Can you identify which family is this? See the very first big jump. First big jump. First big jump. Where is the first big jump, children? See, it's continuously increasing because it's successive ionization energy. IE1 is lowest and IE6 is highest. Yes, Dhruv, the big jump is from first to second. Could you identify, children? The very first jump of thousands. Arnav, second. Good. Ashita? Yeah, good, Bhavya. Lavanya, your answers are not coming faster. Hmm. So how many valence electrons? How many valence electrons? So which family? Children, are you understanding? Only one valence electron. This. Only one. When you remove this, you have hit an inner core. So one valence electrons means family number one. Alkali metals, yes. If I say this is in period number 3, period number 3, the element is in period number 3, you have identified the group number 1, name the element, identify the element. These type of questions are there in AP exam. Are they tough, children? No? Okay, identify this element. It is in period number 2. Element is in period number 2 and the successive ionization energies are mentioned here. I'm just blocking rest of the things so that you can see it clearly. Identify the first big jump. Mhm. After removal of how many electrons, you can see the first big jump. Remember, it has to be, the difference has to be more than thousands, means many thousands. Okay, Sanjana is saying fifth. After removal of 5 electrons or after removal of 4 electrons, Sanjana? Okay, your answer is right that the fifth is big jump. See, children, this is big jump. This is thousand, thousand. So thousand, thousand. This is not a big jump. Big jump is clearly visible. Every time it will be clearly visible. See here, 6 to 38. Big jump, right? So how many valence electrons? After removal of 4 electrons, there is a big jump, correct? So valence electrons are 4. We are good with this? Because no one is answering. So I'm just explaining, right? So which family? Which group number? Fourth group means just ignore the D block. Fourth group is which group? 14th group. 14th. So it belongs to 14th group, fourth group. The head of the family is carbon. So which element is this? Yes, Sanjana. Good. Yes, Shivani. Perfect. So the family is fourth. Period number is 2. Look into the periodic table. Period number 2. 14th group. Because you remember 13th can be taken as third family. If we ignore the D block and do the numbering, then it is third. That will be given to you, Dhruv. One thing will be given to you. Okay. Period number will be given to you. And this data will be given to you. And you have to identify the element. Ready for another question, children? This one. Period number 3. Element is in period number 3. So this time I'll keep quiet. Let me see how many of you can identify the element. Identify the element. Bhavya, any struggle, dear? Bhavya, Veer? Bhavya, you're okay with the answer? Okay, good. That's really fun doing questions. Identify. I love identify things. Identify element, identify compound. It's like a detective work. We are good with this, all of us? Okay, that's the meaning of your successive ionization energies. You can see that for nitrogen. See nitrogen? Nitrogen has 5 valence electrons. First electron removed, second, third, fourth, fifth. After fifth, can you see the big jump, children? 53. 9,000 to 53 for the nitrogen. Okay, check sodium. It has only 1 valence electron. So after removal of first, there is a jump. 495 to 4,000. So that can be taken as big jump. Aluminum. Removal of first, second, third. 3 valence electrons. Can you see the big jump? From 2,000 to 11,000. It's a big jump. So you have to analyze the big jump. You have to understand how to identify the big jump. Right? You can see the big jump in sulfur. Can you see the big jump anywhere? No. How many values are given? 6 values are given. You cannot see here. More data is needed. More. Can you see in the P? The big jump in P? This one. 6,000 to 21. In sulfur and chlorine, you cannot see the big jump because I need more ionization energies. Because sulfur has 6 valence electrons, so big jump will come after 6th electron. Chlorine has 7 valence electrons. You can see in the periodic table. So big jump will come after 7th electron. So that's the story about successive ionization energies, and questions will be there based on it. Yes, Ashita. Now the next concept, we are done with this. Electron affinity. I'm expecting that I can finish it fast. I tell you the reason. Because most of the things which we discussed, the understanding part, the concept with ionization energy, that should help us here. Okay. First of all, electron affinity is the negative energy. Negative means exothermic. Exothermic means attraction, right? Making of attraction. And another, this is also defined on an atom in the gaseous state. So there is an atom A in the gaseous state. I'm adding an electron in this. It gives you, can you tell me what I'm going to get? It's gaining 1 electron. So what is the charge here? Any one of you? -1. It's forming an anion. Let's see what is happening. This is the nucleus, and this is the electron cloud around the nucleus. 1 electron from outside is entering. When it is entering, this electron is going to have a positive attraction by the nucleus. So new attractions are made. So the electron is making new attraction with this nucleus, right? And due to this attraction, there is repulsion also, inter-electron repulsion. But here attraction is more, repulsion is less. So when A is going to gain 1 electron, the electron is going to be attracted by the nucleus, nuclear charge, but the electron is going to be repelled by rest of the electrons. Am I right? Please understand this concept. Electron entering inside the atom, two forces will start operating on it. Two. One, attraction. This is electron. One, attraction. Second, repulsion. When first electron is added, attraction is more, repulsion is less. Okay, because here when the electron is added, there are many other factors is helping in this pairing up. It's helping in getting the inert gas configuration. So many things are there. So attraction is more, repulsion is less. So energy is released because attraction is more. If attractions are made, exothermic, energy released. So electron affinity by definition is energy released when an electron is accepted by a neutral atom. Atom has no charge, no charge. And this is called as electron affinity 1. It has other name also, delta H, electron gain enthalpy. This name is also valid, electron gain enthalpy. Please write it down. Don't get confused. Enthalpy means heat. Delta means change. So when electron is added, the amount of heat which is going to released, this one, you can call it as delta H, electron gain enthalpy. Books are mentioning it. It's negative because it is exothermic, adding first electron. is always exothermic. First electron gain enthalpy, EA1, first, always exothermic. Any question, children, till now? Because now I have questions. You have understood that you are making attractions with the nucleus, the electron is making attraction. So exothermic. If I give you a big atom and a small atom, electron is approaching the big atom, the small atom, and the big atom. This is the nucleus. This is the nucleus. In which case, the electron is going to experience more positive charge in big or small. There is a big atom, there is a small atom. Electron wants to enter in big and small, in which case the electron will experience more positive charge. What about rest of you? Ashita, you're back? In small. Why? Because attraction is more, distance is less. Nucleus is very close by, attraction is more. Bhavi, I'm teaching very important concept. Children, you must, I'm just telling everyone that I know that class is tiring, but you will come into habit of learning. You see that I'm not rushing anything because I know it can be very strong if I do things very fast. So I'm going slow, very slow, and interacting with you. So keep your water bottle because even if you miss a single line, you start getting confused. So try to avoid going out of your chair. Take it like a tapasya, right? Meditation kind of thing. Just whiteboard, my voice, nothing else. So you will see that you will understand better, you will retain more. Okay. Keep your water, some eating material next to you, something to eat, some snacks. Okay. Like sometimes I'm also drinking tea here. Electron gain enthalpy, delta H electron gain. You said when the atom is small, then electron gain enthalpy is high. If I give you two values of electron gain enthalpy, one is negative 1834 kilojoules per mole. Other electron gain enthalpy is negative 800 kilojoules per mole. Can you tell me out of these which value is bigger? Which value is higher? Which electron gain enthalpy is higher? Minus 800 kilojoules or minus 1834 kilojoules? Mhm. Which one is higher? And Veer is right. This one is higher. Why? Because it's not algebra. It is the amount of energy released. This much amount of energy is coming out. And in second case, only 800. So don't take it as an algebra number. It's the energy released. So here more energy is released. And here less energy is released. Let's go to the periodic table. So can I say big atoms, low electron affinity, small atoms, high electron affinity. Can I say that, children? You can write it. This is one factor. So one factor is size. One factor is size. But here also there is another factor, second factor, which is valid across the period. Across the period only. It's not valid down the group. And what is that? Stable configuration, exactly half filled. Stable electron configuration. You know these elements, this one, fully filled, subshell, NS2, NS2. They don't want to gain electrons. They are happy like this. Though they are not very stable, definitely they can gain and lose, but this is fully filled, more stable as compared to others. And this one. So their electron affinity, exactly half filled and exactly fully filled, this one and this one. Please write down their electron affinity is nearly zero. It's a question in the exam. It's nearly zero. I'll show you the graph. And then there is one more exception across the period. This is the exception I'm discussing across the period. This one. This is the exception now. Do you think these elements wants to gain electron, children? They have very stable configuration. Do you think they want to destroy their stability by gaining electrons? That magic number, octet, the inert configuration? No, they don't. So for the noble gases, for these noble gases, I'm writing here, noble gases, it will be difficult to add an electron because their configuration is very stable. So electron affinity for the noble gases is positive value, is endothermic. You need to add heat. You have to force the electron to go inside neon or argon. You're forcing electron. Forcing means you need energy. So noble gases have endothermic electron affinity. Positive delta H. Delta H, electron gain enthalpy, is positive for noble gases and is nearly zero for beryllium family and nitrogen family. This is across the period. But here we have to face another important thing, that down the group there is one exception. Down the group. Children, you are okay with the first factor, second factor? First factor and second factor. First factor size is valid across the period down the group. Second factor, stable electron configuration only across the period. Whoever is stable doesn't want to gain electrons. So their electron affinity is zero. Noble gas is very stable. If you want to add electron, supply energy means endothermic. Then yes, you can force an electron. Otherwise, no. But down the group, there is one exception. So this is so much information. I hope you're digesting it. Is it okay? Till now, everything is okay, children? First and second factor? Anyone confusing? No one confused. Okay. Now let's see down the group. I'm, I have already introduced you one term. You remember inter-electron repulsion? Inter-electron repulsion. Down the group, the first period element, I'm going to compare first element with second element. Only first and second element will show you this exception. Like here, come here on this side, fluorine and chlorine. Let's compare. Fluorine is the smallest element, and chlorine is bigger than fluorine. This is fluorine, this is chlorine. You know what happened? When electron enters in the fluorine, due to it has very high electron affinity, it is the smallest. Small element means very high attraction with the nucleus. So fluorine is expected to have highest, but no. The reason, when electron enters in fluorine, there is more inter-electron repulsion. More inter-electron repulsion. Because of small size, already 9 electrons are there. You are adding one more. So nucleuses are attracting it, but electrons are repelling it. That repulsion is more in fluorine than chlorine. Chlorine is bigger in size. So when electron is entering in this chlorine, attraction is there, attraction with the nucleus, but repulsion is less, right? So here, less inter-electron repulsion. And due to this reason, chlorine is the element with highest electron affinity, not fluorine. Chlorine is higher than fluorine. Sulfur is higher than oxygen. Phosphorus is higher than nitrogen. And silicon is higher than carbon. And aluminum is higher than boron. Is it confusing, children? I can show you the graph, okay, now. So there are three factors. I know that this third factor, maybe you are slightly confused about it. Am I right, Bhavya? You must be struggling with the third factor. So you people are okay with the size factor? Size is okay? Size big, electron affinity less, less negative. Size small, electron affinity is more negative, more value. No, it's a regular trend down the group across the period. But are you okay with this stable configuration like beryllium family, nitrogen family, and noble gases? Their electron affinities are nearly zero. We are okay with that. They don't want to add electron. So nearly zero. Noble gases with the positive. Anyone has any question with the second factor? Any question, children? No question? Third factor is a question. Third factor is valid when I'm going to compare the first element and the second element of every family. Only first and second. Leave hydrogen. First and second. Element of every family. Then the second element of the family is slightly bigger. So inter-electron repulsion is less. First element is very small. It's the smallest in that family. Lithium is the smallest here. Beryllium is smallest. They are smallest in their family, right? Down the group, size increases. So the first element, because it is smallest, very small, it's not going to welcome the new electron as the second element. Second element is slightly bigger. So inter-electron repulsion, there is more space. So inter-electron repulsion is less. So ionization energy of the second elements, this one, is always greater than the ionization energies of the first element. That's an exception. After that, regular trend. Regular as size increases, electron affinity decreases. Children, ask your question, then I'm going to show you some graphs and then we'll work some questions on it. Any question here? Are you okay with this? No questions. Then you are going to answer my questions here on the graph based on those three factors. Okay. I'm not going to confuse you with this something written here, electron affinity and ionization. You just take it as negative energy, okay? Can you tell me? Okay, I'm changing the sign here. Please take it as more than zero. More than zero means positive, and all these are negative values, right? Explain why the electron gain enthalpy of this family is endothermic. Give reason. Electron gain enthalpy of noble gases is endothermic. Means energy is needed. You can write in brief. I explained you 2-3 times. Yes, Lavanya? Noble gases. Please answer. Noble gases have positive electron gain enthalpy. Why? Is there anything special about noble gases, Lavanya? Yes, they are already stable. They don't want to, their configuration is stable. I was writing on the whiteboard there. I was explaining. You people were listening very carefully. But I'm not getting answer now. Stable what, Dhruv? Stable? Stable what? Fully filled, stable configuration. Fully filled, stable configuration. Can you tell me why this nitrogen is zero and this beryllium is zero? Magnesium is zero. Why? Why they are nearly zero? Yes, nitrogen is exactly half filled, doesn't want to gain electrons. And this is fully filled. Remember, I said across the period, you have to work with the stability of configuration also, right? These are questions, tricky questions, but they are very simple if you practice them. Now, the next question, these values are negative. Which one has higher electron affinity? Fluorine or chlorine? Here, answer this question. Arnav, you're there? Answer this question. Fluorine or chlorine, which one has higher value? It's very simple. Values are written in front of you. Why? Which one is bigger in size? Fluorine is smaller. Chlorine is bigger. But you are saying chlorine has higher electron affinity. What is the reason? No, Arnav, chlorine. Chlorine has higher. Arnav, chlorine is going to release 349. It's not algebra. You remember? I said it's not an algebra. It is the amount of energy released. 349 kilojoules released. Negative means coming out. Here only 328. Yes, Bhavya is right. See, she gave me the first answer. Because fluorine is smaller, very small, it has more inter-electron repulsion for incoming electron than chlorine. And you can see the same trend here. Same. Over here. Check. Oxygen has less electron affinity than sulfur. And you can see the same here. Nitrogen has less than phosphorus. Carbon has less than silicon. Boron has less than aluminum. These are very reactive matters. So trend is not very regular, but these are the questions in the exam. They will say which element has the highest electron affinity. Then you will be seeing which one is the smallest. And if you leave this one, smallest is fluorine. So children will say fluorine, but answer is chlorine, not fluorine. See here, compare all the values. This is highest. This value is highest, right? No one is higher than this. So children, interpretation of the table. You remember we spent so much time on zero unit because my aim was that if the table is given, if a graph is given, you should be able to analyze it. Okay, analyze this graph. This is the electron affinity versus atomic number. On the top, who is there on the top? Halogen family. Where are noble gases? You remember for ionization energy, it was noble gases. Where are the noble gases? Below zero. They will be down. See, this is neon. This is, oh, sorry. Yeah, this is neon. And this one is argon, right? And this one is your krypton. This one is xenon, like this. They are below zero. Can you see here? This is lithium. Who is next element? Beryllium. Stable configuration, fully filled, zero, nearly zero. After beryllium, boron. You can see my writing, children. Beryllium here, boron here. This is carbon. Check down here. What is this element? Who is going to tell me what is this element? I'm in period number 2. Lithium, beryllium, boron, carbon, nitrogen. Can you see it's zero? Touching zero. Stable configuration. Doesn't want to gain electron. After nitrogen, oxygen. Then fluorine. After fluorine, a noble gas, neon, below zero. Then after neon, sodium. Then magnesium. See, magnesium fully filled, nearly zero. Aluminum, silicon. What is this? P. P doesn't want to gain electrons, so it has lesser electron affinity than silicon. It's not nearly zero, but yes, it's less. Then chlorine. Compare fluorine with chlorine. You can see chlorine is more than fluorine because of less inter-electron repulsion due to big size. Then after that is a regular trend of the group. Size increases, this is a group, this is a group. Size increases, electron affinity decreases. But in every group, second element is more than first element. This is second, this is first. You can see the difference. Let's see the next oxygen group. Where is oxygen? Here is oxygen. This is oxygen. I'm using a thick pen, oxygen. Can you tell me where is sulfur? In the next silicon, phosphorus, where is sulfur? Can you see increase? Sulfur is more than oxygen. Same reason, big size. Then after that is a regular trend. Okay. Now let's see the next family. I think due to d orbitals, there is some anomalous introduction. So these are missing. But are you okay with this, children? We are understanding this. So that's the electron affinity trend. Read my notes. One last thing about the electron affinity trend. Last. So I'm taking you on the periodic table. You remember that I said for the electron affinity, size is important, but inter-electron repulsion is also important. So that is the reason fluorine is less than chlorine, oxygen is less than sulfur due to inter-electron repulsion. First electron gain enthalpy, very important concept, is always negative. Delta H electron gain negative. Exo. You can call it as electron affinity. Because attractions are made, repulsion is less, attraction is more. But when I go to the second, check here, children, A minus gaining one more electron. Do you think this electron is equally welcome as this one? No. On this A, there is no negative charge. But here, there is a negative charge. This electron has to face too much of electron repulsion. And when I'm adding the second electron, my delta H electron gain enthalpy, the second one, adding second electron, is always positive because inter-electron repulsion is more than attraction. If repulsion is more, attraction is less, it means you are pushing electron, you are forcing electron to go inside. If you are forcing electron to go inside, it means energy is needed. Is it okay, children? So can I say only first electron gain enthalpy is negative? Only first electron gain enthalpy is negative. Please write down. Only first means if you're adding second electron, third electron, they all will become negative means released, exothermic. Negative means released, exo. But more than that, if you're adding second electron, third electron, then it's going to be positive, endothermic. So I will leave you after 1 minute. Okay, don't worry. I know that you are tired. One last question, children, and then we are done with electron affinity. Oxygen gaining first electron, giving you O minus. Oxygen minus gaining one electron to give you O2 minus. Delta H electron gain enthalpy 1. Delta H electron gain enthalpy 2. Out of these two, which one is negative and which one is positive? Mhm. Which one is negative and which one is positive? Answer this question and we can end the class. Yes. Which one is negative, children? The first or second? Hello? Am I audible? Then answer, Arnav. Dhruv, my audio is working properly, I think. Am I audible, children, or my voice was breaking in between? So you're unable to answer this after such big explanation? That's really shame on my teaching. I gave you the complete explanation, everything, and then I'm asking a very simple question and no one is answering. It means the teaching was really bad. So you have to check your audio, Dhruv. The question is here. Which one is negative? This electron gain enthalpy. Which one is negative and which one is positive? And I explained you the first electron gain enthalpy is always negative first. That's what I explained you. Because here repulsion is less, attraction is more. And second electron gain enthalpy is always positive. So children, sometimes I feel that when I give you slightly lengthier explanation and if I ask question after that, I'm not getting right response. So I feel that you're not listening. So please understand that sometimes the explanation they go slightly lengthier. So keep asking question in between. That's the ideal way. Like I'm explaining you something from last 5 minutes and you feel like, oh, she's saying something and you are in the dreamland. Start asking question here. Okay. So please understand this, that it's very important. You should interact with me. You should be asking question. Look, when the way I started the classes initially, so all of you were asking so many questions. Don't let me speak continuously for 5 minutes. Ask questions. Because if I'm continuously speaking, it means you are drifting away. If you're not asking question, you're drifting. You're not listening what I'm saying. That's why you could not answer such a simple question. Okay. So don't worry, review the class, see what I explained, try to understand. So I'll see you then in the next class, children, next week. Okay, Dhruv, what I was saying? The question is which electron affinity is negative and which one is positive? That was the question.